Welcome back to Low-Level Programming Crashcasts. I'm Sheila, and as always, I'm joined by my co-host, Victor. Before we dive in, we'd love to hear from you. If you're enjoying our podcast, please take a moment to rate us on your preferred platform. It really helps us reach more learners like you.
Absolutely, Sheila. Your feedback means the world to us. Now let's get into today's topic. We're starting a new chapter on number systems and data representation, and our focus today is on binary, decimal, and hexadecimal systems.
That's right, Victor. And to kick things off, I have a quiz question for our listeners. Here it is. In what everyday item might you commonly encounter hexadecimal numbers?
Ooh, that's an intriguing question, Sheila. It really makes you think about how these number systems might be hiding in plain sight in our daily lives. I'm curious to see if our listeners can spot where hexadecimal might be lurking. Any guesses, folks?
Indeed. We'll reveal the answer at the end of the episode. But before we dive deeper, Victor, could you give us a brief overview of what we'll be covering in this chapter on number systems and data representation?
Certainly. In this chapter, we'll be exploring different ways computers represent and work with numbers. We'll start with the systems we're discussing today: binary, decimal, and hexadecimal. Then we'll move on to signed and unsigned numbers, floating point representation, and finish up with character encoding. It's all about understanding how data is represented at the lowest levels of computing.
That sounds fascinating. Let's start with the basics. Can you explain what we mean by number systems?
Of course, a number system is essentially a way of representing numbers. It's like a language for numbers, if you will. The most familiar to us is the decimal system, which uses 10 digits, 0, 9. But computers often use binary, base 2, and sometimes hexadecimal, base 16.
I see. So the decimal system is base 10, binary is base 2, and hexadecimal is base 16. But what does base mean in this context?
Great question. The base refers to how many unique digits are used in the system. In decimal, we have 10 digits, 0 to 9. In binary, we only have 2, 0 and 1. And in hexadecimal, we have 16, 0 to 9, and then AF to represent 10 to 15.
That makes sense. So in binary, we can only use 0 and 1. How does that work for representing larger numbers?
In binary, we use place values, just like in decimal, but instead of powers of 10, we use powers of 2. Each digit represents a specific power of 2, and we add them up to get the decimal equivalent. For example, the binary number 1010 would be equal to 10 in decimal.
Oh, I think I get it. So in binary, each digit represents a power of 2, and we add them up to get the decimal equivalent. But why do computers use binary?
Great observation. Computers use binary because it's easy to represent with electronic circuits. A circuit can be either on, 1, or off, 0, making it perfect for binary representation. It's simple and reliable, which is crucial for computer operations.
That makes a lot of sense. Now, what about hexadecimal? Why do we need that if we already have binary and decimal?
Hexadecimal is kind of a middle ground between binary and decimal. It's compact like decimal, but easily convertible to binary. Each hexadecimal digit represents 4 binary digits, making it a convenient shorthand for binary numbers, which can get very long.
I see. So how would we convert between these systems? For example, how would I convert the decimal number 42 to binary and hexadecimal?
Great question. For binary, we divide by 2 repeatedly and keep track of the remainders. The remainders, read from bottom to top, give us the binary number. For 42, we end up with 10 to 10 in binary. For hexadecimal, we divide by 16. The remainders, again read from bottom to top, give us the hexadecimal number. For 42, we get 2A in hexadecimal, where A represents 10.
That's really interesting. Are there any real-world applications where understanding these different number systems is important?
Absolutely. Understanding these systems is crucial in many areas of computing. For instance, IP addresses are often written in decimal, but they're stored as binary. Hexadecimal is commonly used in color codes for web design, memory addresses in low-level programming, and even in some error codes.
Fascinating. Now, I've heard that there can be some confusion when working with different number systems. Are there any common pitfalls we should be aware of?
Good point, Sheila. One common mistake is forgetting to specify the base when writing numbers. For example, 10 could mean 10 in decimal, 2 in binary, or 16 in hexadecimal. That's why we often use prefixes like 0b for binary and 0x for hexadecimal in programming languages.
That's a great tip, Victor. Before we wrap up, do you have any fun facts about number systems?
Here's one. The Mayan civilization used a base 20 number system. They probably developed this system because they counted using both fingers and toes.
That's fascinating. Now, let's reveal the answer to our quiz question. Victor, would you like to do the honors?
Certainly. The answer to "In what everyday item might you commonly encounter hexadecimal numbers?" is color codes. If you've ever looked at the source of a web page or used a color picker, you've probably seen color codes like FEV 1000 Zahlen for red or V100FF0 for green. These are hexadecimal representations of RGB values, which stand for red, green, and blue.
That's right. To summarize today's episode, we've learned about 3 number systems: binary, base 2, decimal, base 10, and hexadecimal, base 16. We discussed how to convert between these systems and their real-world applications. Remember, binary is the language of computers, decimal is what we use daily, and hexadecimal serves as a compact representation of binary numbers.
Excellent summary, Sheila. Understanding these number systems is crucial for anyone diving into low-level programming. It's the foundation upon which much of computing is built.
Thank you, Victor, for these insights. And thank you, listeners, for tuning in. If you enjoyed this episode, please visit crashcasts.com and consider joining our Discord community. Your support on Patreon helps us continue creating this content. Don't forget to subscribe and rate our podcast. Until next time, happy coding.